Sinusoidal forcing happens frequently in systems. It models the shaking of a building in an earthquake or sound waves pushing against glass. We're going to use the methods of last class to solve this forced second order differential equation. So the forcing function is sine of t. So remember last class we just used lucky guess to solve a forced second order equation, forced harmonic oscillator. So you start by just dropping the forcing function and solve the associated homogeneous system. Okay. Then you just have to remember how to do that, right? And so this was a second version of lucky guess, right? You guess y equals e to the st. You're going to get two versions of s, and then you take a linear combination of your two solutions, and that gives you your general solution to the homogeneous. So you can, without having to do all the work that we had been doing for a long time, you can just write down the characteristic equation based off of the differential equation. This is going to be s squared plus 2s plus 2 equals 0. It's familiar, right? Okay. And then I want to solve this. Does it factor? It doesn't, so I have to use the quadratic formula. Sorry, I'm just looking for my notes. Maybe I don't have them. That's all right. Okay, so I got to use the quadratic formula here. So S is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's 4 minus 8 is negative 4. So negative 2 plus or minus the square root of negative 4 over 2. And what's the square root of negative 4? I times root 4, which is 2i. So S is negative 2 plus or minus 2i over 2. Divide that 2 in the denominator into both terms of the numerator, and you get negative 1 plus or minus I. So when you have these S's are actually your eigenvalues. And when you have complex eigenvalues, you only need one of them, right? So I'm going to start with a solution y equals e to the st, and I'm going to use negative 1 plus I times t. And now we're going to practice our methods for dealing with complex eigenvalues. Remember, it is a lot easier when you're dealing with the harmonic oscillator because you don't have to get an eigenvector, and that's where all the difficult algebra comes in. So first I'm just going to distribute this t. So I have e to the negative t time, e to the negative t plus it. And then I'm going to do my little trick that we've done a lot this semester where I rewrite this as e to the negative t times e to the it. Because when you have multiplying like bases, you would add those exponents. So we're kind of doing the reverse of the way you've seen that rule used. All right, so then I'm just copying down the e to the negative t. But then I'm going to use Euler's formula on e to the it. So Euler's formula says e to the I theta is cosine theta plus I sine theta. We're using a t instead of a theta here. So this is cosine t plus I sine t. Distribute your e to the negative t. On the e to the it. Yeah. All right, so the reason I only needed one of the S values was because once I do Euler's formula and I've broken it down into a real part of the solution and imaginary part of the solution, each of those are themselves solutions. Real and imaginary. They are each solution. So I could check, right? I could just take e to the negative t cosine t. It's going to take some product rule, so it's a little bit of work. But you could check that actually will solve the homogeneous system. If you plug y double prime in and y prime and y and add them together, you'll get 0. So will the imaginary part. Again, it takes a little work to take two derivatives because that's a product rule. But you could do it and plug it in and see that it's also a solution. So we actually have two particular solutions here. We could call this y1 and this y2, two particular solutions. To the homogeneous, yeah. We're only working on the homogeneous part right now. Yeah. So my solution to the homogeneous, I'm going to write y homogeneous, is k1 e to the negative t cosine t plus k2 e to the negative t sine t. And we're only like halfway through the problem. We've only solved the homogeneous, associated homogeneous equation so far. Yeah, now we need a y particular that solves the forced equation with the sine t on it. All right, so I'm going to do that on a new page. Everybody's got this? All right, so it was y double prime plus 2y prime plus 2y equals sine t. And I need to guess a y particular. So your guess typically has a form of the forcing function plus each of its derivatives until either you have no more derivatives or they start combining into like terms. Okay. So I'm going to have a sine t. I'm going to have an alpha sine t. And then the derivative of sine is cosine. So I'm going to do plus a beta cosine t. And then the next derivative is going to be sine again, which would just combine into the first sine. So I don't have to keep writing derivatives. So my guess is alpha sine t plus beta cosine t. So to plug in here, I'm going to need a y prime and a y double prime. So I'm going to take two derivatives here. So the derivative of y particular prime is going to be alpha cosine t minus beta sine t. And then the derivative of that, so I get the second derivative, is going to be negative alpha sine t. Derivative of sine is cosine minus beta cosine t. So this is going to take a lot of space to write out, or I might just try to write really small. Okay, so y double prime. I'm just going to copy my y double prime particular. Do it down here in case I need more room. Negative alpha sine t minus beta cosine t. That's my y double prime. Plus 2, my y prime is alpha cosine t minus beta sine t. Plus 2y. Y is alpha sine t plus beta cosine t. And I need that to equal sine t. All right, so I'm just going to combine my like terms, all my sine t terms and all my cosine t terms, and then you equate coefficients. Another name for this method is undetermined coefficients, so that might help you remember how to do it. All right, so I'm going to do a couple of steps in one here. I'm going to distribute and combine like terms. So I have a negative sign here, negative alpha sign, and when I distribute this 2, I'm going to get a negative 2 beta sign, and then I'm going to have a 2 alpha sign. So I have negative alpha plus 2 alpha is alpha, and then minus 2 beta sines. And then my cosines, I have negative beta, 2 alpha, and 2 beta. So I'm going to have a beta. Negative beta plus 2 beta is beta. And then I have 2 alphas. And then I'm just adding a little bit to the right-hand side. There are 3 betas? Yeah. Yes. Yeah, so I set it up so that the left-hand side is some stuff sine t plus some stuff cosine t. And then my right-hand side, I wrote the same way, something sine t plus something cosine t, so that I can now equate the coefficients. So 1 has to equal that, and 0 has to equal that. So I have 2 equations, 2 unknowns. Alpha minus 2 beta equals 1, and 2 alpha plus beta has to equal 0. So this is a pretty easy one to solve by substitution. I think I'll just solve this first equation for alpha, 1 plus 2 beta, and then plug in over here. So 2 times 1 plus 2 beta plus beta equals 0. So that's 2 plus 5 beta equals 0. So beta would be negative 2/5. And then come back over here and get alpha. That's 1 minus 4/5, which would be 1/5. All right, it's kind of a lot of work, but we now have our y particular. Y particular is alpha, what was it? Alpha sine. Alpha sine. So 1/5 sine t minus 2/5 cosine t. Still not done solving the problem yet. I'm mostly done, right? All I have to do now is add my y homogeneous and my y particular, and you have the final general solution. So y general, it was K1, actually let's write down y homogeneous plus y particular, just to remind you. And then y homogeneous was K1 e to the negative t something cosine t, okay. K1 e to the negative t cosine t plus K2 e to the negative t sine t. That's my y homogeneous, and then add my y particular. I don't know if I'm going to have room here. Plus 1/5 sine t minus 2/5 cosine t.
Plus the other way around. Oh.
Yesterday was exactly the same. We're just applying to yesterday's technique to a different kind of function on the right-hand side. But the exact same technique that we learned yesterday or Tuesday. Instead of e to the t's, or we had some polynomial forcing functions. Yeah. Okay, but we're going to learn a new technique now. So I've got several solutions graphed to this differential equation that we just solved. And it looks like they all look kind of different, but then they sort of settle into the same sinusoidal function. And that makes sense when you look at the solution that we came up with, because the homogeneous, y homogeneous, they're sinusoidal, but the amplitude of them are exponential decay functions. The e to the negative t are exponential decay functions. So you see the amplitude starts pretty big, and then they decay. So these terms, both of these terms go to 0. E to the negative t, an exponential will always beat, trig function. So in the long run, those terms go to 0, and you're left with strictly y particular, which is a sinusoidal. And so they start out with these big amplitudes, but then they settle into y particular. All right, so for number 1, I asked you to do it using complexification. I don't care. Just do one of these problems with complexification so you can practice it. You can use the other method too if you like it.